Hello, welcome to Velocity Time Graphs. First of all, just a few definitions, just things that we've probably seen before, either in previous courses or within this course even. First one is acceleration. Acceleration is simply the rate at which velocity changes. Velocity changes. Okay. Now, because velocity is a vector, acceleration will also be a vector. Now, when we say the rate at which it changes, an example of this might be, let's say, something is accelerating at 1 meter per second squared. Now, if something is accelerating at 1 meter per second squared, that means as it's going along, it's getting faster and faster. After, let's say it's starting at rest, 0. After 1 second has passed, it is now moving at a velocity of 1 meter per second. After 2 seconds, it is now moving 2 meters per second. After 3 seconds, it is now moving at 3 meters per second. So it started at rest and it was speeding up at a rate of 1 meter per second each and every single second. Now, in this case, sometimes we have this happening, which means it is non-uniform motion, right? Which is really just motion in which velocity changes. So if the velocity is changing, that could be either magnitude or direction, right? As all vector quantities have both magnitude and direction. Direction quantity. So this non-uniform motion, it could be either the magnitude, meaning the speed, or the direction, if it's going left or right, could be what is changing here. Right, so as we take a look here, if we think about then the instantaneous velocity, it's a measure of velocity at a precise moment. At a precise moment. Now, if you think about this, let's say we're starting at rest and we're speeding up and the car is going faster and faster and faster, and they say right at this precise time what speed it was going. Now, we may have started at rest and been going up to, let's say, 60 kilometers per hour, but 3 seconds in, it may have only been at 15 kilometers per hour, and that is an instantaneous velocity. It's a snapshot in time. Now, everything we're going to be dealing with at this point is uniform accelerated motion. That is where acceleration, or the change in velocity, is constant. The change in velocity is constant. Okay, so everything that we're going to be dealing with, we're only going to be dealing with in where we've only got a uniform change. It is accelerating always at. It's not like speeding up faster at the beginning and slower at the second. Now, just a quick little geometric term as we take a look at this. A tangent line is simply a straight line which touches a curve, at one point. At one point. So let's say if I've got a graph and it's moving like that, this would be my tangent line, and it's actually touching at one point. My diagrams is not really great there. I'm going to redraw that just to make it a little bit easier to see. Let's say there, and we're going to draw a line. Right, there's my line, but it's only going to touch at one point right there. And here's where we can see is my tangent point right here. Okay. So the formula that is associated with this acceleration, which is a vector, is equal to the change in velocity over time, where A is acceleration, V is velocity, and so we've got that delta V, which means change in velocity over time. Standard units for time is seconds. Standard units for velocity is meters per second, and so acceleration is actually meters per second squared. And all of this is related to what we call physics principle 1 on your data sheets, which shows uniform accelerated motion. So everything is going to be dealing with that particular concept. Let's take a quick peek here at an example. This is a graphing example where we've been given the time and displacement, and we need to figure out the displacement at each interval. And so we're not really worried about this because it's for the intervals, and over this interval we have a displacement of 0.02. This interval is a 0.04. We get that from taking 0.06 and 0.02. This next interval from 0.6 to 0.12 is 0.06. And what we see here is with each of these intervals, the displacement is increasing continually. Well, that should be 1, 0. Okay, and so the average velocity given the times, and each interval is 0.2 seconds, means the average velocity goes from 0.1 to 0.2, 0.3, 0.4, and 0.5. We see the average velocity is continually increasing. So we're going to be drawing a position time graph. We need to make sure that we're using even intervals on the axes. Title, very important. Use at least half of the graphing space, please. And we circle our data points. That's just so that we can see it. And we're going to use a line of best fit or a smooth line, not just connecting dots. So let's draw a position time graph for this particular data. And so here we've got our graph. We need to have, and this is a position versus time graph. Total displacement that we saw within that data goes from 0 to 0.3. So we're going to go from 0 and we're going to have to go up to 0.3. And the easiest thing for us to do is make each of these 0.02, 0.12, 0.16. Now I am just actually filling in every other column, but that's all right. That makes the last one 0.38. We've got this as being the displacement, which will be in meters, and it is against time. Time goes for 1 second, so we're going to just make each 4 of these equal to 0.2 seconds. Works nice for our data as well. We've got a little bit of space there at the end. That's all right, and this is in seconds. As we plot these points, we are plotting the displacement. That's this third column. Displacement. That's this column here against time, which is this column here. So this will be placed on our y-axis, and this is actually going to be placed on our x-axis. So the points, if we take a look, the first point is 0 and 0. The next one is 0.2 and 0.02, so that would be here. Next one is at a time of 0.4, and we've got 0.6. That's right here. Then we've got the next one at 0.6 is 0.12, which is here. The next one here, and it's all the way up to 0.2. And this one here, all the way up at the top, 0.3. Now, as you can see, this comes in a line that looks like that. We should be using a smooth line and not connecting the dots.